Hi, this is Professor Jem H. in California State University, Long Beach. In this video lesson today, we'll look at how to sketch graphs of rational functions. I will illustrate the steps through the following example. Notice that we follow these steps when the degree of the numerator polynomial is less than or equal to the degree of the denominator polynomial. If that's not the case, then we need to consider the long division first, and then in that case, we're actually going to have something called a slant asymptote, and that's going to be considered in a separate video. As a rule of thumb, when you're trying to sketch a graph of a rational function, you always have to know where the vertical and horizontal asymptotes are, and the x-intercept and the y-intercept. And behaviors help, also the behaviors around the vertical asymptotes help as well. Occasionally, we have to plot additional points to help us generate a smooth curve. Again, we start with the step 1, which is to factor the numerator polynomial and the denominator polynomial. For the numerator polynomial, I'm going to use 1, 2, and 4, 1. Attach a negative on the 1. This way I get an 8 and a negative 1. When I add those two together, I do get a positive 7 in the middle. For the denominator polynomial, I'm simply just going to use 1 and 2 and attach a negative on the 1 to give me the positive 1 in the middle. I get on top x plus 4 and 2x minus 1. On the bottom, I have x minus 1 and x plus 2. Step 2, I'm going to find the x-intercept. And I know the x-intercept occurs when the y value is equal to 0. But when we're dealing with the rational function, it can only be equal to 0 when the numerator function is equal to 0, which means I'm going to set the top polynomial equal to 0 and solve for x. This means I have x plus 4 equal to 0, or 2x minus 1 is equal to 0. In those cases, I get x equals negative 4 and x equals 1/2. These are my x-intercepts, which means these are the points where the y value is equal to 0. We're also going to find the y-intercepts in this step as well, and in this case, we're going to set the x value equal to 0. This step in comparison is much simpler because if x is equal to 0 in the original rational function, that means wherever x occurs, it's all just going to go to 0, leaving you with only the constant terms. Which means that in this case, the y-intercept is just going to be negative 4 over negative 2, which reduces down to 2. In step 3, we're going to find vertical asymptotes, and these are exactly the points where the function is undefined. And we know that rational function is undefined when the denominator function is equal to 0. So in this step, we're going to set the denominator function equal to 0 and solve for x. So this means x minus 1 is equal to 0, or x plus 2 is equal to 0 in both cases. That means I get x equals 1 and x equals negative 2 as my vertical asymptote functions. Next thing we do is probably the most important thing in this entire process because it helps us determine the shape of the function. And we're going to determine the behavior around the vertical asymptotes by using some test points. Because it actually is going to take a little bit more room, I'm going to do this on the next page. I'm going to first try to copy over my function because when I do test points, I need to figure out the sign, whether or not the function gives a positive or negative value. We're going to draw a horizontal line, imagining this is the x-axis. We found previously that the vertical asymptotes occurs at negative 2 and 1. It helps that if you actually draw in a dashed line to indicate that this is where the vertical asymptote occurs. Next thing we do is to identify test values around these vertical asymptotes. You don't want to pick points that are too far away because I'm going to use negative 2.1 to the left of negative 2. I'm going to use the value negative 1.9, that is to the right of negative 2. I'm going to use the value 0.9, that is to the left of 1, and also the point 1.1 for the value that is to the right of 1. And just to reiterate, we need to figure out whether the function value goes to infinity or negative infinity as x approaches a from the right or from the left. That's why we're picking these test values. I'm going to start from the left all the way to the right. For the first test point of negative 2.1, if I were to plug that back into the original function, y, what sign do I get? When x is a negative 2.1, I would first get a positive sign because negative 2.1 plus 4 gives a positive result. And then I do 2 times negative 2.1 gives a negative number that, and when I subtract 1 to it, it will still stay negative. For the denominator, I have negative 2.1 minus 1, that's going to be negative as well. And negative 2.1 plus 2, it's going to stay negative as well. Overall, I have 1 plus with 3 minuses, which gives an overall result of a negative. What this computation means in words is that the y value goes to the negative infinity as x approaches 2 from the left. You might even want to remind yourself of this result by drawing a arrow pointing downwards towards the negative infinity as x approaches negative 2 from the left. The next test point of negative 1.9, we do the same process by plugging in the x value with 1.9 negative. We'll first get a positive result and then negative, and the first factor from the denominator is going to be negative, but then the second factor from the denominator is going to turn into positive. This has two positive signs with two negative signs, which produces a positive overall output. What this means is that the y value goes to positive infinity as x approaches 2 from the right. We're going to put this on the graph. The third test point, 0.9, we do the same thing. We get plus times plus over minus times plus. This has three plus signs with one negative sign, which means that this is going to be a negative result, which means y goes to the negative infinity as x approaches 1 from the left. And the arrow will be pointing downwards as I go near 1 from the left. Now on to the last test point here. I'm going to have plus times plus, all divided by plus times plus. This produces a overall positive result, which means y goes to the positive infinity as x approaches 1 from the right. So I'm going to draw an arrow pointing up towards the positive infinity as I go near 1 from the right. In step 4, we're going to find horizontal asymptotes. And remember the result that we have from before. When the degree of the polynomial on top equals the degree of the polynomial on the bottom, the horizontal asymptotes is exactly the leading coefficients. In this case, it's going to be 2 over 1. So I get the horizontal asymptote of y equals 2. Finally, we have all the information that we needed to graph this thing. As we're sketching the graph, we need to plot as many additional points as needed to try to make the graph as smooth as possible. When you're sketching, it's up to you how you want to put the information you've gathered before on the graph. For me, I always like to start with the location of the vertical asymptotes and put the behaviors around them. I'm the result of step 3, and I want to locate the x and y intercepts next and go from there. Here I've put in the two vertical asymptotes first. Next, I'm going to put in my horizontal asymptote. Then what I'm going to do is to put in the behaviors around the vertical asymptotes, which means it's going to go to the negative infinity as x approaches negative 2 from the left. It's going to go to the positive infinity as x approaches negative 2 from the right. It's going to go into the negative infinity as x approaches 1 from the left. And it's going to go into the positive infinity as x approaches 1 from the right. Then I'm going to label my x and y intercepts. The x intercepts is negative 4 and 1/2. The y-intercept is at 2. I think now we're fairly ready to put this all together. I'm going to start from the left and move all the way to the right. I know that the graph needs to pass x equals negative 4, and I know that it needs to go to the negative infinity as I approach negative 2. So it should look something like this. For the middle chunk here, I know it's going to go through y value 2 and x value of 1/2, which means it should look something like this. And for the rightmost piece, it's simply just going to do this. The domain of this function is all the x values that are defined. The only two places where the x values are undefined are the locations of the vertical asymptotes, which means that the domain should go from negative infinity all the way to the first occurrence of the vertical asymptote, that's negative 2. And remember, we cannot include these vertical asymptotes in our domain. Union negative 2 to the next occurrence of the vertical asymptote 1, and then union 1 all the way out to infinity. For the range of this function, the middle chunk basically extends out from the negative infinity to the positive infinity. That means the range is a set of all real numbers.